Hi, my name is Asha Kathuria, and this is my Physics 2212 Lab 2 report on lines of charge. As an overview of this presentation, I'll go over an introduction of the experiment and presentation, including the purpose and main results, as well as important concepts necessary in this lab. I'll then go over the experiment and calculations, a computational model, its inputs and results, and I'll finish up this presentation with some follow-up questions. So the purpose of this lab is to analyze the amount of charge on an ordinary object through a line charge model. Here are some main results, which we'll further discuss later in the presentation. So, important concepts. Coulomb's law illustrates the electric force between two charged particles that sit a certain distance away from each other and is described by newtons per coulomb. We'll also discuss the electric field. The electric field is the electric force per unit charge. Similar to Coulomb's law, the electric field is quantified by newtons per coulomb. In this lab, we'll treat line charges as a lined group of point charges. And lastly, we'll discuss the superposition of electric fields. The principle of superposition states that every charge in space creates an electric field at a point independent of the presence of other charges in that medium, and the resultant electric field is a vector sum of the electric fields due to the individual charges. Coulomb's law is given by the given formula. The electric field is equal to the product of the constant k and the two charge quantities divided by the squared magnitude of the distance vector. The electric field is dependent on the shape of the charged object, hence the electric field for a point charge is defined by the product of the constant k and the charge divided by the squared magnitude of the distance. Conversely, the electric field for a rod is equal to the product of the constant k and the charge divided by the distance multiplied by the square root of the distance squared plus the squared length of the rod over 4. More specific to this lab, we'll analyze the relationship between the electric force and the electric field. In this case, the electric force on tape B due to tape A is given by the formula. The electric force is equal to the product of the charge of tape B and the electric field of tape A. On the left of this slide is a diagram of the setup of the experiment. In this experiment, we floated tape B by moving tape A close to it and below it. This data is found from the previous lab experiment. The specific experimental values are shown to the right. The separation distance between the tape is 2.5 E minus 2 meters. The length, width, and mass of tape B are given by 1.98 E negative 1 meters, 1.8 E negative 2 meters, and 1.98 E negative 4 kilograms respectively. Using these values and the previously mentioned formula for electric field and force, I was able to solve for Q, giving me the value of the charged particle. For this lab, I used the GlowScript starter code to generate a computational model to represent this data. In this code, I inputted the mass of the tape from the previously mentioned data, as well as the value of Q in coulombs that I found in the previous slide. I then was able to create a function that calculates the electric field at a certain point from a specified charge. To do this, I just inputted the formula for electric field from the previous slide and returned that value. From there, I inputted the scale of the electric field arrows and the electric force arrow. I was able to calculate the electric field and force on the top tape due to the bottom tape by adding up the forces from each DQ in the bottom tape as they interact with each DQ in the top tape. I then created the arrow for the net electric field. These are the results generated from the code. The magnitude of the electric force is 1.67 E negative 3 newtons, and the magnitude of the gravitational force is 1.94 E negative 3 newtons. To end this presentation, I'll answer the following questions. The only assumption that was made in this experiment was that each U-tape had about the same amount of charge evenly distributed along the length of the tape. In this case, air resistance is irrelevant because tape B is static once it floats, and the second assumption is false as well, because we treated each tape to be a line charge instead of a point charge. As per the questions on the right, if I had modeled each of the tapes as a point charge like the previous lab report, the values would have been skewed. The value of the line charge model is quite larger than that of the point charge model because the point charge model only considers the interaction at a point, whereas the line charge model takes the sum of the interactions of charges along an entire distance. The value that is most likely to be closer to the real value is the line charge model because it takes into consideration multiple interactions over the entire distance of the tape. Thank you.